In this question, we have been given an initial value problem with the derivative function being the same as x plus y, and the initial conditions s of naught being the same as 0 and y of naught being the same as 1. And here we have been asked to evaluate the next update at y of 0.1 given the step size of 0.1 using the single step and the multi-step methods. So for ease of reference, it would be appropriate to first evaluate the exact solution to this ordinary differential equation. So we're able to tell the difference between the exact solution and the approximate solution that we are going to arrive at using either the single step or the multi-step method. And for this simple solution, we could resolve the exact solution as follows. Where given the derivative function as y prime of s, then the same as x plus 1 plus y, so y of naught equal to 1. So if we rearrange this equation to group y terms on one side and x on the other side, we have y prime of x minus y being the same as x. And you observe that this is a linear first order differential equation. And we can actually solve this by using the integrating factor, which is given as dy dx plus p of x, y, being the same as p of x. In our expression, p of x is the same as -1, and q of x is the same as x. And the integrating factor is given as the solution to that is the same as epsilon negative p of x dx, which is now going to be the same as epsilon integral -1, which is the coefficient of y, -1 dx. And this will be the same as epsilon minus x. So if we multiply our differential equation by the integrating factor, we're going to get epsilon minus x, y prime, minus epsilon minus xy equal to s epsilon minus x. Let's call this equation star. And you will note that the key property of the integrating factor is that it transforms the left-hand side of our expression into a derivative of single terms. That is the goal. So if we assume d dx of, for instance, v of xy to be the same as v of x dy dx minus v prime of xy, then if v of x is the same as epsilon minus x and v prime of x is the same as, if we differentiate this, that will be minus epsilon minus x, then d dx epsilon minus x y will be the same as epsilon minus x, which is v of x, dy dx, dy dx, plus v prime of x minus epsilon minus x y. Okay? And now this will reduce to d dx epsilon minus xy being the same as epsilon minus x dy dx minus, it's minus times plus, epsilon minus xy. Therefore, d dx epsilon minus xy is the same as epsilon minus xy prime minus epsilon minus xy. So let's say this is equation star. So you will observe that equation star, this equation is equivalent to this equation, such that this expression can be represented or replaced by this expression, so that b dx y epsilon minus x is the same as s epsilon minus x. And from this expression, if we integrate both sides, then we are going to get integral d dx y epsilon minus x being the same as integral s epsilon minus x. So that this will take care of this. Y epsilon minus x is the same as integral s epsilon minus s dx. So if we solve this integral, as this integral on the right-hand side, we can do this by integration by using integration by part method, which is the same as integral u dv being the same as uv minus integral v du. So in this case, u is the same as x, and then dv is the same as epsilon minus u or minus x. This is x minus x dx. So that du will be the same as dx, and then v will be the same as negative epsilon minus x, coming from this, and this coming from this. So when we substitute all of these expressions into this, then what do we get? So we now see that y epsilon minus x is the same as uv, that will be minus x epsilon minus x minus integral v minus epsilon minus x du by dx. So that y epsilon minus x will be the same as minus s epsilon minus x plus minus times minus integral epsilon minus x dx. So this, once again, will be the same as minus x epsilon minus x. So once we integrate this, so that will be minus epsilon minus x. Okay? plus the constant c. And you already know to integrate this, say u is equal to minus x, for instance, so that du will be the same as minus the x, so that the x will be the same as minus the u. Then we have integral epsilon minus u, where the x is the same as minus du, right? So this will be the same as minus integral epsilon. This is not going to be minus here because we already said this is minus this. So u, this will be epsilon u. Since u is the same as minus x, so then du will be the same as minus du, so dx, so that the x is the same as minus du. So when we substitute this, the x will now be minus du, while u will be the same as minus x. So this will be u du when this minus comes out. So this will now give us minus epsilon u, and we already know that u is the same as minus u, so this will be minus epsilon minus x. Let's see. So that's how we arrived at this. So now that we have this, so we now know we can now compute for c being the constant of integration. And by so doing, we want to solve for y. Now here, y is the same as epsilon minus u. So it means that y will be the same as this entire expression divided by this. So this negative will be off because 1 over 1, this is already 1. Now, epsilon minus x is the same as 1 over epsilon s. So 1 over this will give us, 1 over this will give us epsilon x. So that will now be minus x, epsilon minus x, minus epsilon minus x plus c times epsilon x, since we are dividing by this. So this now will be the same as minus s epsilon minus x, epsilon x, minus epsilon minus s, epsilon x, plus c epsilon x. So this now will reduce to 0 because this will be minus s epsilon 0 minus x minus plus 0 plus c epsilon x. So this will reduce to 1. So that's minus x minus 1 plus c epsilon x equal to y. So if we should apply the initial condition for which s of naught is the same as 0 and y of naught is the same as 1, then y will be the same as minus 0 minus 1 plus c epsilon 0. So this will give us minus here. This will give us 1 minus 1 plus c. So c will be the same as 1 plus 1, which is equal to 2. Therefore, y of x will be the same as 2 epsilon s minus x minus 1. Okay? Now, this is the exact solution. Okay? This is the exact solution. Now, since we have been able to compute the exact solution for the given example, which is y prime of x being the same as x plus y, given at the initial conditions 0 and y of naught being the same as, what is that again? 1, yes. And we know that the exact solution is the same as y of x being the same as 2 epsilon x minus x minus 1. So and we have to resolve y of 0.1. So that is the problem. Since we have been given the step size, the time step to be 0.1, right? Where x tells the time step. Now, at x equal to 0.1, then the exact solution for y 0.1 would be the same as 2 epsilon 0.1 minus 0.1 minus 1. And this will give us an approximate value of 1.210341836. Okay, so it means that the exact solution for this expression is 1.21 all the way. So now we are going to attempt the solution using the approximate method or methods, being the single step and the multi-step. So we want to start using the single step methods. So we start with the simplest, which is the explicit Euler method. And you recall the formula being yn plus 1 being the same as y sub n plus h of f Sn yn. And we already know that f of s y is the same as x plus y. So at n equal to 0, we have y1, we have at n equal to 0, we have y1 equal to y0 plus hf of x0 y0. And y1 is the same as the next update at the time step 0.1. Okay? So we already know the initial conditions being y0 in the same as y of naught, which is 1. And we also know, based on the time step, that the initial condition for s of naught will be the same as 0. So the next step becomes 0.1, and the next step becomes 0.1 plus 0.1, that will be 0.2. The next step will be 0.3. So should we run an iterative process? So each iteration will be in that time step. Okay. Now that we have this is the same as S0. So our next update will be Y1 being the same as Y0. So we already know what Y0 is, which is 1. Then plus h of f, S0 in 0, 1. Okay, so we already know, having the derivative function, so we now have to resolve f of S0, Y0, which is the same as f of 0, 1. And then we know this is the same as S0 plus Y0, which will be S0, 0, plus Y0, 1, which is the same as 1. Hence, Y1 will be the same as 1 plus the time step h, the step size, 0.1 times f of 0, 1 times 1. This will be 1 plus 0.1, which is the same as 1.1. So you can see that our y of 0.1 is the same as 1.1, which is a close approximation to the exact solution. And the difference between this approximate value and this exact value will give us the local error. And should we consider the local truncation errors for individual steps and get the cumulative error value, then that gives us the global truncation error. Good. So with the explicit Euler method, we have been able to estimate an approximate value for the next object. So let us try another method, the improved Euler method. So the improved Euler method. Now, you also recall the formula yn plus 1 being the same as y sub n plus h over 2 f of Sn yn plus f of Sn plus 1 this, comma, y bar n plus 1. Now, I have done this to differentiate between the next update and the predictor, okay? So we're going to take this as the predictor for which we can adopt any of the known methods to solve, the likes of the Euler method or whichever, and then this becomes the corrector once we plug it in. Okay. Now, at n being the same as 0, we can evaluate the predictor, or the predictor. And here we said that the predictor, let's apply this first. Y bar n plus 1 is the same as yn plus h of f Sn yn. And we have called this the predictor, which is the Euler formula. And at n equal to 0, then the predictor yn plus 1 will be the same as y0 plus hf s0 y0. Okay, and we already know that y0 as given is the same as 1, s0 is the same as 0, h is the same as 0.1. These are the initial conditions, that's step size, and these are the initial conditions. So y0 is the same as 1 plus 0.1 f of 0, 1. And this is going to give us 1 plus 0.1 times, now our function f of x, y is the same as x plus y. So s0, y0 will be 0 plus 1. And this will be the same as 0.1 times this, that will be 1 plus 0.1, right? So our predictor will be the same as 1.1, as earlier estimated. So the corrector at n being the same as 0 will therefore become the improved Euler formula, which will be y1 at n equal to 0, being the same as y0 plus h over 2, f of s0, y0 plus f of s1, y bar 1. So we already estimated this, which is, for which this is when n equal to 0, so this is y1, right? Y, no. So we already estimated that value. So at this point, y0 is 1, which is given as the initial condition. We know the step size, 0.1 over 2. Now, f of the initial value of x, 0. And for y, the initial value is 1 plus f of s1. We already know the step size. That's at 0.1. Then at this 1.1. Okay. So if S0 is the same as 0, then S1 will be the same as S0 plus H, which is 0 plus 0.1, which will be 0.1. Then S2 will be the same as S1 plus H, which will be 0.1 plus 0.1, which will be 0.2, and so on. Okay? So with this, we can now evaluate F. We can evaluate this and this using the formula. So we know this is going to be x plus y, for which x is 0, y is 1, and at this point, x is 0.1, y is 0.1. So this is going to give us 1 plus 0.1 divided by 2, 0.05, into bracket 0, that is 0 plus 1 plus this equation, 0.1 plus 1.1. Okay. So this is going to give us 1.2 plus 1, right? So this will give us 1 plus 0.05 into bracket 1 plus 1.2. So this will be 1 plus 0.05 times 2.2. And now y1 will be the same as 1 plus 0.11. y1 will be the same as y 0.1, which is required to be computed in the same as 0.11. Using the improved Euler formula. Well, it's approximate. It's an approximate value, which is close to the exact value of 0.12 as previously evaluated. And then one more method for the single step approach is the fourth order Runge-Kutta. So applying fourth order Runge-Kutta method, that's RK4. We can split this board. Split it. So you recall the formula to be yn plus 1 being the same as y sub n plus h over 6 k1 plus 2k2 plus 2k3 plus k4, right? And we know that k1 is the same as the derivative function f of Sn yn, K2 is f of Sn plus h over 2, then yn plus h over 2 K1, then K3 is the same as f of Sn plus h over 2, yn plus h over 2 K2, and K4 is the same as f of Sn plus h, then yn plus h K3. Okay. So at n equal to 0, we have y1 being the same as y0.1, which is required for the next time step, will be the same as y0 plus h over 6 into bracket K1 plus 2K2 plus 2K3 plus K4. Okay. Now, so that K1 at this point, for which n is the same as 0, will be the same as f of S0 plus Y0, which will give us, let's place it first in the derivative form. Let's place that in the derivative form. The S0, comma, Y0, right? At this level. So we know our initial conditions. So this will be the same as f of 0, comma 1, right? And then recall the equation. So this will give us 0 plus 1, which is equal to 1. So K1 is equal to 1. Now K2 will be the same as f of S0 plus h over 2, comma, y0 plus h over 2 K1. So this is going to give us f of 0, which is S0, plus 0.1, which is the time step, over 2, comma, y0 is 1, plus the time step, 0.1 over 2 times K1 times 1. All right? Well, we can try to look for that in bracket to get this mixed up. Now, this will be the same as f of 0 plus 0.1 divided by 2. That will be 0.05, 0.05, comma, then 0.1 divided by 2, which is 0.05 times 1 plus, that's 0.05 plus 1, that will give us 1.05. So if you recall, S0 plus Y0 being the function, so that will be 0.05 plus 1.05 when applied to the derivative function. So that will give us K2 to be the same as 1.1. So the next thing now is to evaluate K3, which is the same at F0, which is the same as F into bracket S0 plus H over 2, comma, Y0 plus H over 2 K2. So this is going to give us F of 0 plus 0.1 over 2. Then we have 1 plus 0.1 over 2 times, this is K2, times K2, which is 1.1. Okay. So this is now going to give us F 0.05, comma, then this is going to give us the 0.05 times 1.1, then plus 1 will give us 1.055. And we now have to apply this to the derivative function, which is S0 plus Y0. and that will give us 0.05 plus 1.055, and this is going to give us 1.105. So K3 is the same as 1.105. And then you can now evaluate K4, which is F of S naught plus H, Y naught plus H, K3. So this is the same as F. S naught is 0 plus 0.1, which is H. Y naught is 1 plus 0.1 times 1.105. Okay. So this is going to give us F of 0.1, comma, 1.1105. And once we apply this to our to our derivative function, which is given as x naught plus y naught, let's assume it was 2x naught plus whatsoever. So that's what we apply these parameters to. So this will be 0.1 plus 1.1105 as K4, and K4 will be the same as 1.2105. Boom. So the next point is to apply K1, K2, K3 into this and the initial condition. So we already know that Y1 is the required Y of 0.1, which is the next update based on the next time step. So this is going to give us Y naught, which is 1, plus H over 6, which is 0.1 as given, divided by 6 as the step size, into bracket K1. K1 is 1 plus 2 times K2. K2 is 1.1, 2 times 1.1, then plus 2 times K3. What is K3? 1.105 plus K4, 1.2105, bracket close. So this is going to give us 1 plus 0.1 divided by 6 times the sum, which is 6.6205. And this is going to give us 1 plus 0.1103417. Yeah. So Y1, which is the same as Y 0.1, will be the same as 1.1103 all the way approximately. So that Y 0.1 is 1.1103, which is an approximate value close to the exact solution. Okay, so now let us look up some of the methods using the multi-step approach. Using multi-step methods. Now, we have the Adams-Bashworth method. And you will recall the formula as y of n plus 1 being the same as y sub n plus h over 2, the two-step method, 3 f of Sn yn minus f of Sn as this yn minus 1. Now, for this two-step method, we actually require two initial values, okay? And since y1 is the same as 1.1 as estimated, we could compute this using the Euler method or even the Runge-Kutta, fourth order Runge-Kutta method, okay? And then you realize that the Adams-Bashworth method is not applicable until the second step is computed, because at n equal to 0, we have y1 being the same as y0 plus h over 2, 3f s0 y0 minus f, that will be s minus 1, y minus 1. Okay? So it means we need to evaluate this initial step, and we do not have these values because the initial conditions we have is at S0 equal to 0 and Y0 equal to 1. So, and for us to be able to resolve this, we need the parameters for these two steps. So we have this, but we do not have this. Hence, this solution may be derived numerically using software like the likes of MATLAB or Python, rather than using the analytical approach. Okay? So at this point, we are stuck, but we are going to look up how it is implemented using the MATLAB. Okay? So now, before we pull up to the MATLAB interface, let us look up the Adams-Moulton method. So we'll come back to this using the MATLAB. So the fifth one is Adams-Moulton method. Now, you'll recall for the two-step implicit method that yn plus 1 is the same as yn plus h over 2 into bracket sn plus 1 yn, that's f, yn plus 1 plus f of sn yn. Now, you'll also observe that yn plus 1 appears on both sides, okay? Making this method implicit. So we can actually solve this iteratively. So let's take n to be the same as 0. So we can estimate y1 being the same as y0 plus h over 2 f of S1, Y1 plus f of S0, Y0. Okay. And then we already know the initial conditions. Y0 is 1, S0, Y0, we know them. Okay. So from this, Y1 will now be the same as 1, which is Y0, our initial conditions. The step size is 0.1 divided by 2 into bracket f. Now we know S1 based on the step size. So if S0 is 0, based on the step size of 0.1, S1 will be 0.1. So 0.1, but we don't know Y1. That is required. Plus, we know S0, f of 0.1. So we know this, okay? And we know that the derivative function f of xy is given as x plus y. So once we implement this here, so we have y1 to be the same as 1 plus 0.05 into brackets 0.1 plus y1 plus 0 plus 1. So with this plus this, that will be 1.1 plus y1. So this will be y1 equal to 1.1 plus, let's say, 0.05 into bracket 1.1 plus y1. So we can actually open up this bracket. So this y1 being the same as 1 plus 0.05 times 1.1 plus 0.05 y1, right? And then it should be y1 minus 0.05 y1 being the same as 1 plus 0.05 times 1.1. So this is going to be 1 plus 0.055 being the same as 0.95 y1. And 0.95 y1 will be the same as 1.055. So y1 will be the same as 1.055 divided by 0.95. That will be approximately 1.1105, which is the same as we derived using the one-step method, a single-step method, same as 1.1105. Okay. Now, in a similar vein, we can actually apply the MATLAB or Python applications to solve this, to resolve or better still estimate the required update using the Adams-Moulton method, largely because this method is equally iterative. So come to that. So let us look up one more method before we try to apply or better still utilize the MATLAB software for or demonstrate the implementation of the solutions using the MATLAB software. So we have the backward differentiation formula. Okay. So 16th point here for the multi-step method is the backward differentiation formula, which is BDF, right? And for the one-step backward differentiation formula, we already know that it is the same as the backward Euler method, which is given as yn plus 1 being the same as yn plus h of f sn plus 1 comma yn plus 1. Okay, so this can also be solved iteratively because we have yn plus 1 on both sides. So at n equal to 0, we have y naught or no y1, n is 0, that's naught plus 1. So I can just designate y1 being the same as y naught plus h of f s1 comma y1. So in the same way, we can evaluate this. So y naught is 1 plus 0.1 times f of 0.1 comma y1. And if we apply this to the derivative function, 0.1 times 0.1 plus y1. Okay, so this is going to give us 1 plus 0.1 times this, so that will be 0.1 times 0.1 plus 0.1 y1, right? So this is going to give us, this will give us 0.01 plus 1, that will give us 1.01 plus 0.1 y1, the same as y1. So y1 minus 0.1 y1 is the same as 1.01. We have 0.9 y1 is 1.01. And then y1 will be the same as 1.01 divided by 0.9, which is approximately 1.1222. Okay, so super. So now you see how we have been able to apply the different approaches to resolve the solution using the single step and multi-step methods. So how do we apply the MATLAB software using to resolve the same solution? So now we want to share the MATLAB interface. Okay, good. So the first here is the Adams-Bashworth method. Okay, and on this, you see that. Okay, let us put this up. You see that here we have initialized the time step, because at this point, let's put up this comment. We're given a function f of x, y to be the same as x plus y. Okay. And then the step size was given as this. Okay. So percent sign. This is our step size. And then we have our time points, okay? X being the time points, which we can as well say, okay, let's put that up. This is the time points X, for which the initial value is 0 based on the time step, based on the step size. The next point is 0.1, then the next step is going to be 0.2, 0.3 in that order. So we can actually say it's a vector containing all the points where y of x will be computed. And also we already have the initial condition specified, which is y0 being the same as 1. And now this is the ODE function, which represents the derivative. And then we initialize the Euler based on the formula. So the next update will be the same as this, being the same as this plus this, and the time step times that factor. And we already described the derivative function. This is function. Okay. So, and then we have the next update for the Adams-Bashworth given us this, and then we display the result. So once we run, once we hit the run button, you see that we got 1.23. 1.23. And the exact solution was 1.21. Okay? Now, and this 1.23 is now this is two-step method. So we need to take note of something. This 1.23 is at y being the same as 0.2. Okay? 0.2. So how do we arrive at the value at 0.1? Okay? This is required. Now, being that this is two-step, so this is going to give us the solution for the first step, and this is the second step, okay, which is the result we just got here, okay? Now, for us to be able to do this, we can actually modify this by specifying the iteration, okay? So let's wipe this. And then we now have this. So in the same vein, we have been able to initialize the time step. And here you see that we've been able to specify the step size. Okay, so we have the initial condition and then the derivative function. So with this, we are able to estimate the initial value using the Euler's method. We can also do this using the Runge-Kutta method. And then we provide the iteration, okay? So with this, we are able to establish at what interval, and the iteration starts at the second time step, okay? So with that, so let's put up a little comment here. Yeah. This specifies the iteration loop starting from I being the same as 2, since the first 2 steps, which happen to be y of north, and then y 1 have been computed. Okay, so that has been computed. So we know y naught being the initial condition. We've computed y1 with the Euler's method. And now with this, we can estimate the next step, being the second step. And then we display the result. So this is the 2-step. This is the 2-step Adams-Bashworth Method. And once we run this, then we are going to get the 3 values: the initial value, the expected value, estimated value at y, y of 0.1. So this is y naught, which is the initial value. This is y of 0.1. And this is what we estimated earlier, which is y of 0.2, okay? Based on this time step, okay? And you observe that is what we got in our previous simulation, which is this, right? Okay. That's okay. Now, let us look up the Adams-Moulton method. So with the Adams-Moulton method, we actually run through the same process, whereby we specify the step size, then we also specify the time points, then the initial condition, and the derivative function. And also, we specify using the for loop the iteration. So we are starting at I being the same as 1 in this iteration process. Then afterwards, we provide the predictor, which is given as our Euler formula, and we can actually do same using Runge-Kutta, okay? And then the corrector is the same as the Adams-Moulton method. Then we provide, in this case, the tolerance, okay? So in this simulation, we are providing the tolerance, total tolerance of 1 exponential minus 6. Okay? And with this, we have the maximum iteration. We don't want it to exceed 100 iterations. And here we initialize the iteration. Okay? And with the while loop, we are able to provide an absolute value for the difference between the initial and the next step. And if that is greater than this tolerance value, and this is logic and the iteration is less than the maximum iteration, then whatsoever is predicted is the same as the correct value. That is the previous step. The predicted value becomes the next step. And the next step, which is the correct value, is given by this expression, which is the backward Euler's method. And then we can have our iteration given, then we have the next update, and then we display our result. Okay, so let us have this. So you see, this is the same as what we evaluated analytically, which is the same as 1.1105. So it means that our analytical solution for the Adams-Moulton method is the same as what we got from simulation. And also, we can, okay, let's clear this. And now we also have this, and once we run this, we now have the same thing we did using the Adams for the Adams-Bashworth method. So now we have, using the for loop, we have been able to define the iteration point to start at the second point, so that we are able to get our values for y of naught, y 1 or 0.1. Let's be very specific. 0.1 and then y of 0.2. So with this, we can literally evaluate which is more accurate, okay, in terms of approximating the solution to be as close as possible to the exact solution. Okay. So we have this. So we can run through the total tolerance here, and we have the maximum iteration. So while the initialization of the iteration is less than the maximum iteration, then we evoked the solution, and then we take the absolute value, difference between the next step and the previous step. If it's less than the total tolerance, then we break, and then the next value becomes the same as the new. Then we have the iteration point, and then we print our solution. And the last of them all here in our methods, well, not necessarily the least of them all, is the backward differentiation formula. So with this, we have done the same thing, define the step size, the time point, the initial value, the ordinary differential function, which is a derivative function. We have equally, since it's an implicit method, we have equally defined the iteration points using the for loop, and then define all of that. Then we've given the tolerance, the maximum iteration, and the initialization. And then with the backward Euler method defined, and by estimating the difference between the initial and the next step, if it's less than the tolerance value, then we can break and then establish our update. And once we print this also, so see that this is equivalent to what we also derived analytically.